Recording started. Okay, let's get started on our lecture. So today we will finish a tiny bit about the birth of the stars and then start talking about the evolution of sun-like stars. So first, some review questions. Which star cluster is younger? Let me open the poll. So you see an HR diagram in the plot, asking which star cluster is younger. Yes. So it's luminosity versus temperature, and there's two lines here that indicate where the stars are distributed for that cluster on the HR diagram. Okay, I have finished answering. So here is your votes. The correct answer is B, and most of you got it. I'll explain a little bit why that is the case. I mean, the reason is that the massive stars are at the top of the mean sequence, and they have short lifetimes compared to stars at the bottom. So that for a star cluster, that is the top part of the mean sequence is missing because those stars live very short lifetime, and so they have died after some time. But the low mass stars will still be remaining on the mean sequence, so that it will form this kind of shape. And you can see cluster B still have more massive stars than star A, than cluster A. So star B, these stars in cluster B has not died, so that B must be younger. How old is this star cluster? Another poll. This here is where the mean sequence is, and here is the clusters distribution, and here is the position of the sun. Okay, thank you for answering quickly. Most of you got it correct. It is older than 10 billion years. Because that in this cluster, you see there's no stars like the sun again anymore in this cluster, because the sun is over here, and in this cluster, there's no stars that are like the sun. And so that means that if there probably were such stars in this cluster a long time ago, but those stars have died. Stars like the sun have died in this cluster, and so they no longer exist. So that this means that the age of the cluster must be older than the lifetime of the sun on the mean sequence. The sun spends 10 billion years on the mean sequence of this cluster must be older than 10 billion years. And so if you have trouble understanding this, I think most of you actually don't have any trouble with this. Just here, I'm giving an analogy to say that if we try to plot the height and weight diagram for humans, just like the eye chart diagram for the stars, and you mark a person's height and weight on such a diagram, you can see how we evolve, right? And then similarly for stars, you can mark the luminosity and temperature of stars on an HR diagram and mark and track how it evolves. So here, just using this to illustrate what we mean by evolution on the HR diagram. So the height and weight for a person is low when a person is born, and then it gradually grows larger and larger in both height and weight, right? So in the first year, a baby will grow a lot in height and weight, and then gradually, and then in the childhood, you grow a lot to 4 to 5 feet and heavy in weight, and then this is teenager, you get to your almost your maximum height, and then you grow very slightly after that. And so you see that you moved all this track through the first 22 years, and then you stay here at a very stable position in both height and weight for a long time. So if you consider what is the mean sequence position of a human, it's actually at this location, right? People are mostly 5 or 6 feet or 7 feet high, mostly between 5 and 6 feet, right? And sorry, this is in English units, but anyway, you understand that. And it's several, more than 100 pounds or something. And then you stay at this position for a long time. So it's from 22, 32, 42, 52 years old. You're always at this place and staying roughly at the same place in the diagram for a long time. And so this is like the mean sequence position for humans. And for stars, that's where stars stay. And then maybe after 2 years old, and maybe a person will have a midlife crisis and get overweight but not change the height a lot. So this is sort of the evolution path of a person in the height weight diagram. So for a star, what a star do is that it moves its positions in the HR diagram in terms of luminosity and temperature. So when a star is formed, it does not start on the mean sequence, start somewhere cold. And when a star is first formed, it is not as hot as when it starts hydrogen burning. When it starts hydrogen burning, it will get onto the mean sequence. That marks the birth of a star. So the protostar stage will last about 30 million years, a very short amount of time. And then once the star gets on the mean sequence, it stays here for a long, long time. It does not evolve along the mean sequence, okay? It stay put. It stay at the same place on the mean sequence for a long time. So if you see this age indicator over here, 1 billion years, it is here. 2 billion years, it still at the same place. 3 billion years, same. 4, 5. This is what our sun is today. It is 5 billion years. And 5 billion years old, but we'll have another 5 billion years of time to go on the mean sequence. So it stay at the same place for a long time. 6, 7, 8, 9, 10. And now after 10 billion years, it will actually start evolving away from this. So you see it goes to 10.2 billion years, becomes a red giant. We will talk about this process in a little bit today. And then this stage actually goes through pretty quickly, and so after 10.2 billion years, it just dies as a white dwarf. And so that you see that the star spends most of its time on the mean sequence. And that is why most stars we see are on the mean sequence, because this is where they spend most of their time. And so that if you just look at a random sample of stars, most likely you're going to find these mean sequence stars. So for a star that is much more massive than our sun, it has slightly different evolution. And we'll see that also in our following lectures. And so that we take it only 3 million years to get onto the mean sequence, and then stay there for a little while, 1 billion years. It's only 1 billion years, only stays on the mean sequence for 1 billion years because it has a much shorter lifetime. And then it evolves to a red giant, and then also dies as a white dwarf. So that's how stars evolve. And sort of, so now hopefully you understand a little better of the concept of why massive stars sort of the mean sequence is not evolution sequence. Okay, the evolution sequence is different. The mean sequence is the sort of an apparent sequence that is formed by the stars for different stars. It is actually a mass sequence, and there's high mass stars at the top and low mass stars at the bottom. And for a star cluster, it's just the top half is missing because those stars have died. Okay, more polling questions. To see through the dust in the interstellar media, at which wavelength should you conduct your observations? Please answer as full. If you will answer, please answer the call quickly. Okay. You can see most of you got chose C, and that is the correct answer. Infrared light is how we can see through dust more effectively, because dust particles are small, and so they block light that have wavelengths smaller than short. If the wavelength is shorter, is shorter than the size of the dust, then it will get blocked. But if the wavelength is longer than the size of the dust, then it can go through. So for example, in this picture of this nebula, you can see that there is these dusty columns, and these regions are very, very dusty. It blocks the background light. And if you take an optical image, you see the dust. If you take an infrared image, you can actually see a totally different thing. And you can see you can almost make out the shape of these three columns over here. You can see this is one column, this is another one, and this is a third one. But you can see it is actually very different. In the middle of these dust columns, you can actually see some stars that is shining through it. And these are actually the portal stars that is actually formed in the middle of these dusty molecular cloud. And so this is taken in using infrared light. Because infrared light have a longer wavelength, they can get around the dust and still and shine towards us. So that's why we use infrared light to look at dusty regions. And so next question, star formation begins in what kind of clouds? It seems this is now a harder question. The correct answer is C, is cold molecular clouds. You have to, I mean, the star can only form in very dense place, right? You have to, the cloud has to collapse to form a star, because star is much denser than gas, right? And how do you make the cloud get denser and denser? Gravity will help you to make it denser. However, there is pressure inside the cloud. Basically, as this cloud shrinks, the gravitational potential energy gets converted to heat, so the cloud will heat up. And the only way to and when it heats up, it provides pressure against gravity, so you can no longer collapse, right? The gravity is not that strong when it is sort of a gas cloud. It's if you have pressure inside, it actually cannot continue to collapse. So you actually have to release that pressure out so that the gravity can continue to make it collapse. And how do you make it how to release the heat so that to reduce the pressure is that you have to radiate away the energy. And the clouds can radiate away the energy by these atomic transitions and molecular transitions, right? Because there's atoms and molecules that can hit each other collide with each other, so they get excited, and then they make some radiation, and then they radiate away the energy, and then their temperature goes down. When their temperature goes down, they will the pressure will reduce, so that the gravity will make it more compact. That you have to reduce the pressure inside in order for the gravity to take effect to make the cloud collapse into a star, right? But to reduce the pressure, you have to reduce the temperature. So so star formation will make the cloud collapse. If you are in a hot cloud, for example, a diffuse hot cloud, and the pressure is too high, the gravity will not be able to make it collapse. Even cool atomic clouds will not be able to do that, only in the coldest place where molecules can form. Because molecules have lower energy than how would I say that? That when the cloud is too warm, atoms are moving too freely, and they cannot combine together to form molecules. And when it is when temperature gets really cool, then atoms can combine together to form molecules. So for example, if you heat up a molecular gas, it will actually break up. The molecular bonds will actually break up to individual atoms. So that only in the really cold places we will form molecules. So where you have molecules, you have a really cold clouds. So cold molecular clouds is where you don't have enough pressure to resist against gravity, so that the gravity will make a star to form in those places. Last one for reviewing. Protostar. A protostar's luminosity is generated by what process? Okay, seems you are pretty evenly split on this question. Half of you say gravitational contraction, the other half says molecules radiating at discrete wavelengths, and some of you say fusion in the core. The first, I want to say that it's not fusion in the core, okay, because it's still not a star yet. It's a protostar. So it hasn't. If it started fusion in the core, then we'll call it a star. It's not fusion in the core. So is it gravitational contraction or molecules radiating at discrete wavelengths? The correct answer is A, it's gravitational contraction. It's not molecules radiating at discrete wavelengths. So in the process I just described for the previous question, I described the molecules radiating to radiate away the energy so the cloud can collapse. But at that stage, we don't call it a protostar yet because the star hasn't formed. You need molecules radiating away the energy in a cloud so that they can form a protostar in the middle. But once it forms a protostar in the middle, basically in the very middle, you have a very dense clump of material. It becomes optical, it becomes opaque to light. And at that time, we have a protostar. A protostar, so that it is now basically completely opaque to light. I mean, light is not easy to get out of it. So that at that place, it's no longer a molecular cloud anymore. So a protostar is different from the molecular cloud that formed it. So when the molecular cloud was dense enough, it collapsed to form a protostar. And how the protostar produces energy, it actually by gravitational contraction. It gradually contracts more and more and when it contracts, it actually heats up. The protostar itself actually heat up. The gravity is, at that time, the gravity is much stronger than the gravity in a cloud, because the protostar can still radiate away some radiation, but that radiation actually radiates away in the form of a black body radiation, not as these discrete wavelengths anymore. So it will have, say, several thousand K, a few thousand K of temperature, and it gradually gets smaller and smaller until the center heats up to the point of heats up to the temperature of 10 million Kelvin, then it can start hydrogen fusion. So this process is gravitational contraction. And so that's what produces a protostar's luminosity. Okay, that's all the polling questions. So stars like to form in groups. So this is just one little bit for the burst of stars. And usually when you have a large gas cloud, you don't form just one star. The cloud will break up or fragments into many smaller pieces. And each of these will form a dense center. And then in the dense center, the cloud collapses to form a protostar. So you form several protostars at a time. And if the cloud is very, very large, you can form hundreds, thousands, or even millions of protostars. And that is why we have star clusters. So here, as I showed you this picture last time, this is a picture of a Pleiades. It is an open star cluster. We call it open because the star density is not very high, and you can tell them apart easily. And these stars in an open cluster, they actually are not gravitationally bound to each other. The gravity between these stars are not strong enough, and they will actually gradually fly away from each other. But in a globular cluster, the gravity is strong enough, it will actually hold them together for a much longer time, so that they will stay together. So you see in this cluster, you have millions of stars, and they are densely clustered. So the gravity is strong enough, so these stars will not easily fly away. Of course, some of the stars will still be able to fly away. So here is a computer simulation showing how a small cluster, a star cluster form. At the beginning, it was just a gas cloud, and the gas cloud has some density variations. And you can see that some parts get denser, and that's why indicated by yellow colors. And gradually you will start seeing these little dots coming away from the cloud, because when a star forms, they are so compact, the cloud cannot stop them. If they have any star with any velocity, they'll actually move away from their birthplace. And some of them will actually come back because there is stronger gravity, so some of them are bound to the cloud. But some other stars, if they have high enough velocity, they actually fly away to other places. And you can see these remaining stars, they are gravitationally bound to each other, and they just form a cluster. So this is sort of how we try to understand star formation. We use computer simulations, and it starts with some gas cloud, and then when the gas in it gets dense enough, it will form stars. So there's a question from Trinto asking, can stars collide during the process of cluster formation? And if they do, what happened to them? Stars, in principle, yes, they can collide, but the chance is still very, very low, because a cloud is a huge thing, but a star compared to a cloud is very, very small. Just think about how big is the solar system compared to the size of the sun. The size of the sun is very small compared to the size of the solar system, right? So even in a cluster where the density of stars are much higher, it is still pretty difficult for stars to collide. So it's still very rare. It does happen. It can happen. I think that the chance in a star cluster where the density is high, those things could happen, but it's not. It doesn't happen that often. So they don't have a lot of stars colliding with each other. They can come a short distance from each other and have a strong gravitational pull on each other, so they change their orbits, but they rarely have head-on collisions just because their size are so small compared to the separation between them. Okay, so that's about the birth of stars. Now today we're going to start talking about the evolution of stars, and the evolution of stars is really interesting story because it's a fight between pressure and gravity, and you see that is the main theme through the stellar evolution. It's a constant computation between pressure and gravity, and you have seen that already. That is in the protostar stage. That is gravity trying to pull the cloud towards a single point and where to form a star, but the pressure inside is resisting. You have to relieve the energy through radiation until it gets really, really cold, and then the cloud collapses to form a star. But once our star is formed, once it becomes opaque to light, it can actually trap the heat sort of more effectively, and then the center of it heats up, and then the pressure gets higher. It started resisting gravity, but it will get denser and denser until it starts hydrogen fusion. So it's a constant war between pressure and gravity. So how do we really study stellar evolution? It's actually a very difficult job because our human lifetime is too short. We only live about 100 years, right? And that is very short time compared to a star's lifetime. And for example, the sun's lifetime on the mean sequence is 10 billion years. And that is so much higher, so much longer than our human lifetime. We cannot keep watching a star and to see how it evolves. We cannot follow an individual star's evolution by monitoring it. Even for the most massive stars, the most massive stars will still have, if it is 100 times the mass of the sun, its lifetime is still something like 10,000 years or 100,000 years. And that is too long a time scale for us to keep track because we don't live that long. And our human civilization has only been several thousand years, and we cannot watch individual star evolve. So how do we study it? The way we study is to look at lots of stars of different ages. Just like if you say an alien come to Earth and trying to study the human evolution, so to see how humans grow. They don't have to stay on Earth for 100 years to understand how humans grow, right? Then they can just take a look at a lot of people. They see, okay, there's some babies, there's some children, there's some teenagers, there's some adults, and there's some people who are old. And they can just look at these the human populations and can figure out, oh, these people must grow from small to large, and then get old. So this is how, so they can look at the population of human beings in order to understand human evolution. So for stars, the same thing. We just look at lots of stars because they're at different ages. Then we can try to understand how they evolve. And also we can use physics and run computer simulations to understand how they evolve. So another thing is that stars can have different masses, as you have known already, that stars with low mass have a much longer lifetime than stars with high mass. And these high mass and low mass stars also have very different evolution paths. So we actually need to separate the stars into several groups in order to talk about their evolution. So we'll first talk about low mass star evolution, basically stars like our sun. For stars with the mass that is less than 2 times that of the sun, it have roughly the same story of evolution as the sun. So we will just use the sun as an example to talk about low mass star evolution. Then we will talk about intermediate and high mass star evolution. They have a different evolution paths. So first we will talk about the sun, how stars like our sun evolve. To talk about that, we first need to talk about the composition of the sun. When the sun is first formed, its composition is about 70% hydrogen and 28% helium and 2% of other elements. And this is very similar to the composition of the gas at the beginning of the universe. When the universe first formed, that you have about this much hydrogen and this much helium and a small fraction of heavy elements. And so as the sun, as fusion goes on in the center of the sun, how does this composition change, right? Because sun is fusing hydrogen into helium, so I would not even pose this as a poll because it's too easy a question. Of course, the hydrogen fraction is going to go down, right? Because some of the hydrogen is going to be turned into helium, and the helium fraction is going to go up. So basically, in the center of the core, in the core of the sun, you have hydrogen fusion in it basically builds up in the core of the star, in the core of the sun. So we say here is a fraction of hydrogen and helium, and we plot it as a function of radius from the center of the sun, which is 0, to the outside, where this is the surface. So see here is the horizontal axis. The horizontal axis indicate where in the sun you have this fraction. So at the beginning of the sun, when the sun is first formed, it has the same fraction everywhere throughout the whole body of the sun, and everywhere there's about 30% helium and 70% hydrogen. And what is the situation today? This part is the core. This part is where the temperature is high enough. So within the 0.2 solar radius in the center, in the core, you are turning some hydrogen into helium. So the helium fraction gets higher, and and as helium ash builds up, it accumulates more towards the center, so that at the very, very center, you have a high helium fraction today than what it is the initial helium fraction. So today in the core, we have something like 40 to 60% of helium, and the remaining is hydrogen. And the sun will go on for another 5 billion years until a point when the center become completely dominated by helium. So today, the helium already make up 50%, and then eventually 5 billion years later, it will make up 100% of the core. And when that is happening, something will evolve. So this, actually, we will track the life cycle of the sun like stars using such a table. And we go through many different stages in the evolution process. And there are different phases, and in each of these phases, we'll talk about what is the principal fusion reaction, and also what is whether it has gravitational contraction or not, and also what kind of event is indicate the end of that phase. So if you're taking notes, then you should put a table like this in your notes. But anyway, I will share the slides so you can copy the table later or refer to the slides later. So we have already talked about two rows of this table, the first two phases. The first phase is the protostar phase, right? I mean, this you can also argue that this is not part of the star. This is before our star is a star. So it's why we call it a protostar. But anyway, we list it here. This is the time before it is born, basically. And in this stage, there's no fusion reaction in the star, but there is gravitational contraction, and that is what's producing the luminosity of a protostar. It's by gravitational contraction. And the event ending that phase is the onset of fusion in the core of the protostar. So at the center of the protostar, when the temperature is hot, enough, when it is 10 million kelvins, it will start fusion of hydrogen into helium. And that marks the beginning of a star. And when that happens, the star goes on to the mean sequence of its life, and it stays there for a long, long time. It spends most of its lifetime on the mean sequence. And during this process, turning hydrogen into helium in the core, okay, this part is important, not just hydrogen and helium, but it's doing that only in the core. You'll see later on that the fusion does not necessarily happen in the center. It can also happen in other places of the star. And in this process, there's no gravitational contraction, right? Okay, this makes this clear that there's no gravitational contraction today in the sun. Gravitational contraction was hypothesized as a possible energy production mechanism for the sun, but if it were doing that, it wouldn't last 10 billion years, right? It would only last several hundred million years, and that is too short. So that we proved that hypothesis cannot be an energy production mechanism for the sun. So there's no gravitational contraction in a mean sequence star. What event ends this phase is the exhaustion of hydrogen in the core, right? In the core the helium fraction gets to 100%, then you can no longer turn hydrogen into helium anymore. So this marks the end of that phase. So what happens when the hydrogen in the core is all used up? When that hydrogen is used up, what happens to the core? Right? Remember that when the sun is having nuclear fusion, the pressure provides the resistance to gravity, right? So the pressure and gravity is balanced. There is gravitational equilibrium. But when fusion stops, it can no longer hold that pressure. If when fusion stops, the first thing is that the temperature will drop, right? Because you're no longer producing energy in the center. The temperature will drop because those energy is being radiated away as luminosity through the surface of the star, right? And so that as temperature drops, its pressure is going to drop. And then the pressure from above, basically all the gravity, all the weight of the mass from the outer layers is want to fall toward the center. And they will force the core to contract. It basically will compress the core to a smaller size. And so that at this time, when the helium becomes 100%, basically when hydrogen is exhausted in the center, the helium core will contract. And as it contract, the potential energy gets converted to thermal energy and heats up the core. Excuse me. And the helium core will get hotter and hotter, and also get denser at the same time. It gets denser and hotter. And it has to do this in order to maintain the pressure against the gravity. And the top layers is going to come down, and the more it comes down, the stronger a pressure it will apply to the core, because now the material are at smaller distance toward the center, right? So that the radius is shrinking, but the top part, the mass is still the same, and so that the force gets stronger. As the radius of the core shrinking, that the gravitational force from above actually, the weight of the material from above actually gets higher because the gravitational force gets stronger. So it gets denser and hotter. It has to get denser and hotter in order to maintain the pressure against the stronger gravity. And so what happens just outside the contracting core? The shell will get hotter too. So see here, I'm using the blue to indicate the core and the orange to be the shell. And just outside the core, these material actually now fall toward the center, right? Because the core has contracted, and so these material will follow the core and get smaller places. And so these material is now in the place where the core is used to be. And so at that place, the temperature is high enough for hydrogen fusion to start, right? So basically, although the core is completely made of helium, it cannot do nuclear fusion. But the material that's from above is not in the position of where it used to be hot enough to fuse hydrogens, right? So those material will start hydrogen fusion. So basically the hydrogen just around the core will start a fusion reaction. And this is so in this case that you not only you have a gravitationally contracting core that turning some gravitational potential energy into heat, but also you have a nuclear fusion around the core, turning hydrogen into helium. So basically the core will get small, but it will actually becomes two layers. So you have a contracting helium core in the very center where there's no fusion, but then but around it you have hydrogen fusion in a shell around the core. So you have two energy production sources. The gravitational contraction in the core is producing some energy, and also just above the core, it is now hot enough for hydrogen fusion to begin. So you have hydrogen fusion in a shell around a gravitationally contracting core. And so you have two energy production sources. And with these two energy production sources, you are actually producing more energy than what the star is used to be doing. And the energy production now gets much faster than the outward transfer rate of energy as well. So previously, when it was on the mean sequence, there is an energy balance. How much energy is being produced in the center can all get out in the form of luminosity, right? How much energy is produced per second, all those energy gets radiated away through light by the star. But in this case, the center is becoming much hotter. And it is producing more energy because it has these two energy production sources. But it's not going to be, the luminosity of the star will not react that fast because the star is so thick and it's very, very opaque, right? For the light to go from the center to the outside, remember that it takes them millions of years for a photon to scatter among the electrons and until they can get out to the surface and then escape from the star. So you actually have a limited rate of energy transfer within the star. So that although you produce a lot of energy in the core and around the core, those energy cannot get out so easily. So they will get out gradually, but that transfer rate of energy is not high enough. But you're producing so much energy, so that heats up the center even more. And and it also heats up the shell of the star. So the whole star basically gets heat up, but because of there's a bottleneck of energy transfer towards the outside, it actually causes the star to expand because the inner part gets so hot, and so the pressure gets stronger and becomes stronger than the gravity's pull on the outer surface, and actually pushes the outer layer outward. So that is how the star will expand into a giant star. The overall luminosity will still get higher because you are anyway producing a lot of energy, so that it will become a balanced state that eventually that the luminosity also gets higher to balance the energy production, but the star has already expanded. So you have a huge luminosity due to the huge energy production rate, but it will have a cool surface because of the size of the star has expanded so much, right? So remember, the luminosity equals to the surface flux times the surface area, right? The surface flux is going according to the Stefan-Boltzmann law. The surface flux goes as temperature to the fourth power, and the surface area goes as radius squared. So the luminosity is increasing gradually, but the size is expanding by quite a bit. So although luminosity is increasing, it doesn't increase as fast as the surface area. The surface area gets much larger, much faster because of the bottleneck of energy transfer, and so that the temperature of the star will actually drop because the luminosity is only going up a little bit, but the surface area goes up a lot, so that the temperature has to drop to compensate for the increase in surface area. So where would the star move on the HR diagram is that its luminosity is going to get higher because it now has two energy production sources, right? One is the gravitational contraction in the core, another is the hydrogen burning around the core in a shell. But the star has expanded so much to become a red giant, and so the temperature will actually get a little redder. So it initially was at 6,000 K, now it's going to become to go to about 3,000 K. So it grows to become a red giant. And here is a picture of a star cluster where you can see lots of red dots. So this is globular cluster Omega Centauri. It's in the constellation Centaurus. And you can see that there's lots of blue stars, tiny dots, but these big red things, look actually much brighter than the other stars because they are red giants. They are huge, and also they have huge luminosities, but they have cool surface, so they look red. Okay, so a red giant have a, compared to the mean sequence phase of that star, it is now cooler on the surface, but more luminous overall. Okay, and so that is consistent because that their sizes are not so big, right? So they have a less surface flux, but they have a higher surface area, a much higher surface area. So overall, their luminosity is not higher. So that is this phase of the sun-like star evolution. It is in the red giant phase. We call it a red giant, and it has fusion reaction in it, but that fusion reaction is not in the core. Okay, the core is a helium core, and it has not yet started fusion yet. Where hydrogen fusion is, it is in a shell around the core. And where do you have gravitational contraction? Yes, it has gravitational contraction in the core, in the helium core. So this is this phase of the stellar evolution. And then we'll talk about what event marks the end of this phase next time. Thank you very much. That's it for today. Yeah, we'll upload these notes shortly after. Thank you.
Thank you. Bye-bye.